All right. So we're moving into the last unit of material for this course. And for the last unit, we're going to talk about some things that I think are really pretty interesting, different than other kinds of math that you've likely encountered in your life before, but also, some applicable things to real life. So the first concept that we're going to talk about are graphs, graph theory, but not graphs like when you graph a function. Instead, we're going to be dealing with things like this, graphs like this. So for the next 3 lectures, we'll be talking about these kinds of things. And then after that, we'll talk about things like voting and apportionment and things like that, which are very applicable for your real-world lives, I would say. Graphs are also applicable in real-world situations. Not that you necessarily in your career will be working with graphs, but people work with graph theory for all kinds of things like logistics, computer science, things like this. So anyway, let's get into it. So for the purposes of graph theory, a graph is just something that consists of a finite set of points called vertices. And by the way, that vertices is plural. The singular form of vertices is just vertex. Okay. Anyway, so a graph consists of a finite set of points called vertices, singular vertex, and lines that we call edges. Okay, so it's made up of vertices and edges. You can have a vertex with no edges coming out of it, but you can't have any edges without vertices, right? The edges always have to join a pair of vertices. So that's kind of the rule that we set for ourselves with graphs. Anyway, so this would be a picture of a graph. As you can see, we normally label the vertices with capital letters, in this case A, B, C, D, E. And if there's only one edge connecting 2 vertices, then we can label that edge by the vertices that it connects. So for example, this edge here that connects vertex A to vertex C can just be referred to as AC or CA, whichever way, it doesn't matter. However, if there's more than one edge connecting 2 vertices, then it would be confusing to call that edge by the vertices that it connects because it would be ambiguous as to which one you're talking about, right? So in that case, we will just usually label the edges with some kind of lowercase letters. So for example, it would be confusing to refer to edge AB because notice that there's one edge connecting AB that's like this straight line, and then there's this other kind of curvy edge connecting A and B. So we have 2 edges connecting A and B. So if you just call it like edge AB, it's like which one are you talking about, right? So instead, we might do something like label this one E1 and label this one E2 so that you know which edge you're talking about. And by the way, if I haven't made it totally clear yet, this doesn't work the same way as normal geometry. So you might be thinking the segment that joins A to C, this edge, is the same as the edge that joins C to E. It's just one straight line. But that's not true for graph theory. In graph theory, we consider this edge that joins A and C to be completely and totally different from this edge that joins C and E. In fact, when you're dealing with graphs like this, you're allowed to kind of like move edges around and stuff, as we'll see in an example below. Okay. So the point with graph theory is not so much to focus on like distances or anything like that. So this is completely, it's a figure that you should think of as being totally malleable. You can take the points and kind of move them around as long as you don't break any edges or anything like that. So anyway, so let's talk about, and let me just say maybe one more thing. The reason for this is because what we're really interested in when we're looking at a graph is we're interested in relationships. We're not really interested in magnitudes or like, again, distances, anything like that. We're just interested in relationships, right? Things that connect, say, A to D or whatever. Okay. So one of the things that we like to do with graphs is we like to see if we can trace them. To trace a graph, means to begin at some vertex and draw the entire graph without lifting your pen or pencil and without going over any edge more than once. You may have seen puzzles like this before, right? So to give you an example, let's try with this graph up here. Let's place our pen or pencil on any vertex of the graph above and see if we can trace the graph. So so I'm going to do this in pencil so that I can erase if I need to. But for example, if I start here at vertex D, you know, maybe I can go up to A, and then I can go, oh goodness, I don't know, down to C, back down to D. Now I'm not allowed to go over the same edge twice, but I can pass through the same vertex more than once, so that's fine. So that worked out pretty well. Maybe I'll try to do the same thing there, and I can go back down, and then I can use this kind of curvy edge to come around. Okay, so now I'm going to run into some trouble, right? Because if I go from here to here and try to come back and get the curvy edge, now I don't have a way to escape. Well, but then again, I can't go back, so I only have one choice. I've got to move forward, either this way or this way, but I'm going to end up at the same spot either way. I suppose I could come back and go there now, but there's no way back. Go back there now, and now I'm definitely trapped. So I failed to get that top edge. Shoot. I got all the rest of them, just not this very top one. Well, so try again. Go ahead and give the video a pause and see if you can trace this graph. See if you can trace it. I'm going to move on though. So I'm going to go ahead and just move forward. Okay, so graphs can be a bit tricky to wrap your brain around. Actually, they're not that tricky. If you gave a graph to a kid, like kids totally understand them. But because you've been used to like algebra and geometry, right? Your brain has kind of been messed up. Not messed up. It's just you're used to thinking about things in certain ways. Like I said, you're maybe used to thinking of this entire segment as one thing. But in graph theory, it's not. We really have one edge going from here to here, and then another edge going from here to here. They're two different edges. Okay. So they're not like the normal geometric figures you're used to. You're allowed to move vertices and edges around as long as you don't pull an edge out of a vertex. So as long as you're not like pulling the thing apart. So consequently, a point of intersection is not a vertex unless we actually specifically draw a solid dot there. So for example, these two graphs are really drawing two ways of drawing the same graph. It's kind of weird, but this little point of intersection is actually not a vertex because there's not a vertex specifically drawn there, and so it's not a vertex. Okay, and you can kind of see how they get from here to here. They've taken this edge joining A and C, it's right there. They've taken this edge joining C and E and kind of made it a little curvy. They took the edge joining E and D and put it right there. They took the edge joining D and B and made it this kind of curvy little part. And then to redraw the figure so that you don't end up with this sort of false intersection, they took this edge joining C and B, made it just a straight line, and then they took this other edge joining A and D and they drew it as this curvy line. So now there are no, or this curvy edge. But it's the same thing. You have the same relationships, right? Here A is connected to C, B, and D. Here A is connected to C, B, and D. And the same thing for every other vertex. So these are the same graph, right? They're the same exact graph, just drawn in a different way. Okay. So as we'll see over the next few lectures, graphs can be used to model all kinds of things in the real world. For example, one of the famous problems that served as an impetus for the development of graph theory is the Koningsberg Bridge problem. The Koningsberg Bridge problem is this, right? So 7 bridges connect the 4 portions of Koningsberg as pictured below. So you've got like a landmass up here, landmass down here, a couple of little islands in the middle, and you've got bridges, right, connecting these land masses together. I think in the original statement of this problem, it was something like, there are pubs on each, section of land, and somebody wants to get to all the pubs without crossing the same bridge twice or whatever. Something like that. Anyway, we'll do it a little more innocuously, I guess, and just say, is it possible to start from some point in the city, cross each bridge exactly once, and end up back where you started? So at first glance, that might not seem like a graph theory problem. I mean, it's not a graph, right? However, if we treat each portion of the city as a vertex and each bridge as an edge, then we get the following graph. So we can turn this thing into a graph. So each landmass will be a vertex. So we'll have vertex A, vertex B, vertex C, and vertex D. And I'm just arranging them into a diamond shape kind of arbitrarily. You could arrange them however you want, really. But we need a bridge joining A and B. So maybe I'll label these A, B, C, and D. So we need a bridge joining A and B. We need a bridge joining A and C. We need another bridge joining A and C. Okay, that takes care of all the A bridges. Then we need a bridge joining B and C together. Then we need a bridge joining B and D. And then two bridges joining C and D. That's the graph that we would get out of that. Okay, so now answering part of the Koningsberg problem is just a matter of figuring out if we can trace the graph. Okay, if you can trace the graph, then it's certainly possible to get from one place to all the other places without crossing the same bridge twice. The only part of the problem we haven't answered, I guess, is, can we end up back where we started? And that's something that we'll talk about. But really, the question is, can we trace the graph? Well, turns out there's a good way to figure out if a graph is traceable, but it requires a few more definitions. So by the way, if you paused the video a second ago and you were trying to trace out this very first graph here, and you were like getting really frustrated because you couldn't figure it out, it's because this graph is not traceable. And we'll talk about why. Okay, but first we have to give some definitions. So a graph is connected if it is possible to travel from any vertex to any other vertex of the graph by moving along successive edges. A bridge in a connected graph is an edge such that if it were removed, the graph would no longer be connected. Connected graphs are sometimes called networks, and so you can kind of see why this would be useful in, say, computer science. But anyway, this is a connected graph. This is not a connected graph. Okay. So basically, a non-connected graph would be like if you took two graphs and put them together and did not join them together with any edges, right? Then you've got a disconnected graph or a non-connected graph. This is a connected graph. CD is a bridge because if you removed CD, then you would end up with a disconnected graph, right? ED is not a bridge because if you removed ED, you still have a connected graph, right? You can still get from any point on the graph to any other point on the graph. Okay, so that's connected. If you remove CD, it's disconnected, and so CD is a bridge. No other edge in this graph is a bridge. This isn't even connected to begin with, so it doesn't make sense to talk about bridges. Okay? All right. Next definition. The degree of a vertex is the number of edges joined to that vertex. A vertex is odd if it has an odd degree, and even if it has an even degree. So let's look at a couple examples, right? And we'll answer the question, is this graph connected? List its odd and even vertices. What is the degree of G? Are any edges bridges? Well, let's see. So is the graph connected? Can you get from one vertex to any other vertex just by traveling along edges. And by the way, when you're answering the question whether or not the graph is connected, that's not the same thing as answering the question whether or not the graph is traceable, right? To be traceable, you have to be able to travel over all the edges without going over the same edge more than once, okay? To be connected, you can go over the same edge multiple times if you need to, right? And so anyway, this is connected for sure. I don't have any pieces that are sort of like floating out by themselves anywhere. I can get from B to F, for example, by going like that. So yeah, this thing is connected. So is it connected? So yes, it's connected. We're told to list its odd and even vertices. So odd vertices, let's see. Well, A has two edges, 1, 2, coming out of it, so A is even, B is even. C has 1, 2, 3 edges, so C is an odd vertex. D is even. G has 1, 2, 3, so G is also odd. F only has 2, E only has 2, so those are even. So the rest of them are even. So A, B, not C, D, E, and F are all even vertices. Okay, what's the degree of G? Well, we said it a second ago when we decided that it was odd because it has 1, 2, 3 edges coming out of it. So I'll call that degree of G equals 3. And then finally, are any edges bridges? Oh yeah, I see one. If we remove AB, that's not a big deal. That's still a connected graph, right? If we move that edge. If we remove EF, same thing, not a big deal, still a connected graph. But notice if we remove GC, if we remove this edge right here, now you get one graph that's ABCD, and then you get another graph that's EFG, right? It's like a triangle within a square, and they're disconnected because you've removed this bridge. So the answer is yes. So we'll say yes, edge GC is a bridge. Okay, let's do another one kind of like that. Is the graph connected? What are the degrees of A, C, and F? I don't know, I had some kind of printer malfunction or something. List the odd and even vertices. Okay, is the graph connected? Almost. But we've got this vertex here that's not connected to the rest of the graph. So the answer is no. So F is disjoint from the rest of the graph. So it's not a connected graph. But that's okay. What are the degrees of A, C, and F? So the degree of A would be 2, right? 2 edges coming out of A. Degree of C would be 1, 2, 3, right? 3 edges coming out of C. Degree of F would be 0. There are no edges coming out of F, so 0. Then it says to list the odd and even vertices. Well, we've already decided that C is an even that C is an odd vertex. So C for sure. B, 1, 2, 3 is also odd. Even, A is even. F is even, if we consider 0 to be an even number. So A, D, E, and F are all even vertices. Okay, so that's that. All right, so hopefully we're kind of getting the idea, getting the hang of these graph things. So now let's talk about how to decide if a graph is traceable. So the result that tells us whether or not a graph is traceable is called Euler's theorem. And I know that's, you look at that name and you think there's no way that's pronounced Euler, but it's not English, right? Euler was not I don't know what nationality he was, but he wasn't an Anglophile, right? He wasn't someone who spoke English, or maybe he did speak English, but the point is he was from like I don't know, the Netherlands or something. Anyway, or Germany. But but the way you pronounce his name is Euler. So like oil, right? Euler. So it's not Euler, it's Euler. Okay? Euler's theorem says a graph can be traced, so it's traceable, if and only if it's connected and it has 0 or 2 odd vertices. Okay, so it's traceable if and only if it's connected and has 0 or 2 odd vertices. So that's crazy, right? If you have more than 2 odd vertices, then the graph's not traceable. This fact can be deduced from the following observation. Suppose that A is a vertex on a traceable graph. If A is neither the starting point nor the end point of the trace, then A must be an even vertex. Okay, why? Well, because we know that the graph that A is a vertex on is a traceable graph, which means that once you arrive at A via some edge, there has to be another edge that would allow you to escape, right? And if there were, say, a third edge coming in, then since you've already traversed these two edges, there would have to be another edge to escape. And the same way, if you keep adding new kind of pathways leading up to A, there has to be another pathway leading out of it, because A is not an end point. It's not the starting point or the ending point of any of your traces. It's just some point in the middle, or some vertex in the middle. And so there always, if there's some way leading into A, there has to be a way leading out, which means that this is always going to be even, right? The degree of A is always going to be even. Okay, so if A is a vertex on a traceable graph, then the degree of A has to be an even number. Has to be. Okay? Unless it's a starting point or an ending point. If it's a starting point, then it could have one edge. It could just have one edge kind of leading out of it. Or if it's an ending point, it could just have one edge leading towards it. Or it could have, like, if it's a starting point, you start there, you go, somehow you end up back in, and then you come back out, right? Then you have still an odd number of vertices. So that's okay. If it's a starting point or an ending point, this situation is okay. But if it's some point in the middle of your trace, it's got to be an even degree. Okay, so that's where Euler's theorem comes from. And it tells us very clearly whether or not we can trace a graph. So determine which of the graphs can be traced. Note that part A is the graph from page 1, and part B is the Koningsberg graph. We didn't draw it quite this way, but this is just another way to draw the Koningsberg graph. Okay, so determine if the graphs can be traced. So remember, if the graph can be traced, then each vertex has to be even. You can have 0 odd vertices, or you could have 2 odd vertices, but you can't have any other number of odd vertices. Okay, so if I look at this one, I've got 1, 2, 3, 4, 5 edges coming out of it. So now that's not necessarily game over, because you can have 2 odd vertices and the graph is still traceable. So here we have 1, 2, 3, 4, 5. Okay, degree of B is also 5. Again, that doesn't necessarily mean game over, because you can have 2 odd vertices as long as the rest of them are even. Here the degree is 1, 2, 3, 4, 5. Now it's game over. Right? You have more than 2 odd vertices. This thing is not traceable. It's not traceable. So not traceable. Okay. What about the Koningsberg problem? Okay, so can we cross all 7 bridges and end up back where we started or whatever? Well, let's see. Degree here, 1, 2, 3 is 3. Not necessarily game over. Degree of B is 1, 2, 3. Okay, not looking good, but still not game over. Degree of D, 1, 2, 3. Okay, now it's game over. Right? And just for the fun of it, degree here is 1, 2, 3, 4, 5. So this one's not traceable. You've got more than 2. You've got more than 2 odd vertices. Okay, let's look at another. Part C. Okay, so number of edges. I've got 1, 2, 3, 4. Okay, that's good. For B, 1, 2, 3, 4. Still looking good. For C, 1, 2, 3. Okay, that's all right. What about D, 1, 2, 3? Okay, we're still in the game. What about E? 1, 2, 3, 4. Okay, so I have 2 odd vertices. The rest of the vertices are even. So this one's traceable. It's traceable. Let's see if we can figure out how to trace it. Now that's another question altogether, but since it's traceable, using the kind of reasoning that we talked about up here, we know that we're not going to start at an even degree, at an even vertex. We should start at an odd vertex. So I might start at, so like I know that my odd vertices have to be my starting and end points. So maybe if I start at C, I have no idea how this is going to go, but I can go this way and this way. And oh, I've painted myself into a corner already. So I'm going to go this way, then over this way. How about that? Is that better? Yeah, I think I can make that work. So then I can come back this way and then back down. Then I'll come all the way back over to A. Then I'm forced to come back around here. Now what? Oh, I can come over and then up and then around. And there's my endpoint. See? So see how the odd degrees, those are, it's like they're forced to be the starting and end points if you have any odd degrees. But there you go. That one's traceable. And we just traced it. Okay. One more. So is this one traceable? Pause the video. See if you can figure it out on your own. Here's my solution. For A, I've got 1, 2, 3, 4. So that's okay. For B, I've got 1, 2, 3, 4, 5, 6. So that's okay. For C, I've got 1, 2, 3, 4. That's okay. For D, I've got 1, 2, 3, 4, 5, 6. That's okay. And for E, I've got 1, 2, 3, 4. 1, 2, 3, 4. And that's it. So on this one, all of the degrees are even. So that's definitely traceable. And since all of the vertices are even, you could start with any of them. Probably. You could start with any of them and trace out the thing. I'm not going to try to do it for you. I'll let you kind of figure that out. If you want to pause the video and see, well, I know that it's traceable. What is the trace? You know, you can give it a shot. By the way, more than one right answer. So in terms of like how to trace it out. But that's that. Okay. So we've decided, we figured out how you can tell whether or not a graph is traceable. But just because it's traceable doesn't mean that you end up where you started. In fact, this one that we traced out just a second ago, we couldn't end up back where we started, right? We started here and ended there. So that leads to an interesting question. Like, if a graph is traceable, when is it possible for you to end up where you start? Well, so let's talk about that. So a path in a graph is a series of consecutive edges in which no edge is repeated. Okay, the number of edges in a path is called its length. By the way, a path doesn't necessarily have to try to get anywhere in particular. It's just a series of consecutive edges. So for example, BACF is a path. Or BACFDG is another path, right? These are all paths. Okay. The number of edges in a path is called its length. So the path BAC would have length 2 because you only go over this edge and this edge, so 2 edges. Okay. Okay. A path containing all the edges of a graph is called an Euler path. Okay, so really an Euler path is another name for a trace. What we've been calling a trace is really an Euler path, right? Because a path is a series of consecutive edges in which no edge is repeated. So you don't go over the same edge more than once. And an Euler path contains all of the edges of a graph. So it's just a trace. It's just synonymous with trace, okay? An Euler path that begins and ends at the same vertex is called an Euler circuit. A graph that contains an Euler circuit is called an Eulerian graph. Okay, so a bunch of terms there. But the big one is Euler path and Euler circuit. An Euler path covers all of the edges exactly once. An Euler circuit covers all of the edges exactly once, and it ends up back where it started. Okay. If it's possible for you to draw an Euler circuit on a graph, then that graph is called Eulerian. Okay, and so now a graph is Eulerian if and only if all of its vertices are even. So as we saw in this example, this graph has an Euler path. It does not have an Euler circuit. Okay, it's not possible for you to end up back where you started, and the reason is because you have these two vertices with odd degrees. This graph, on the other hand, all of the vertices were even. Okay, so that means that this graph is not only traceable, right? Not only does it have an Euler path, it actually has an Euler circuit. So this graph is Eulerian, right? Okay. So in other words, a graph contains an Euler path if and only if it has 0 or 2 odd vertices, and it contains an Euler circuit if and only if it has 0 odd vertices. So you're not allowed. So to have an Euler circuit, you're not allowed to have any odd vertices. Okay. So let's give an example. So let's find an Euler path in the graph below, and then let's answer the question: does this have an Euler circuit? Well, I guess we could ask ourselves, does it have an Euler path, first of all? It might be helpful to answer the second question first, actually. So notice that the degree here is 2, 2. Here the degree is 3. Okay, so right off the bat, I know that it doesn't have an Euler circuit, right? So note the degree of vertex C is 3. So there's no Euler circuit. Could be an Euler path, though, maybe. Degree of F is 1, 2, 3, 4. Degree of D is 2. 2, 2. By the way, this is not a vertex. 2 and 1. Degree of h is 1. So there are two odd vertices, h and c. That's okay though. That means that there must be an Euler path, because you're allowed to have two odd vertices and still have an Euler path. The only thing is that we have to start at one of the odd vertices. So we have to start at C or we have to start at H. And it doesn't matter which one. So I might start at C, work my way around. Now what? Well, I know I have to end at H. So if I go down this way right now, I'm going to be stuck. I'm not going to be able to get back up. So I really have two choices. I can either go up to D or over to E. Let's guess this way. Oh, that worked out nicely, right? And then down and then over. And there you go. Okay, so there's an Euler path. Now what did we do? We started at C. We started at C, and then we went to A, and then we went to B. By the way, this is the way that we describe paths, is that we just write down the vertices in order. So we C, A, B, then back to C. Then we went to F, then we went to D, then we went to G, then we went to E, then we went to F, then we went to I, and then we went to H. That was our Euler path. Okay. Very good. So, note that although Euler's theorem tells us whether or not Euler circuits exist in a graph, it doesn't tell us how to find them, right? It only tells us whether or not they exist. And finding them can be tricky. It can be a little bit challenging. So we're going to talk about a way that we can find Euler circuits called Flurries Algorithm. And actually, I don't know if that's the way that you say that name. I didn't look that name up. Euler is famous, right? Euler shows up in math all the time. Like the number E, which you may have heard of before. It's like 2.7-ish. That's called Euler's number. So Euler was a very prolific mathematician. He did a lot of stuff. I've never heard of this person before. So I don't know how to say this person's name. I'm going to call it Flurry. Okay, Flurries algorithm. So if a connected graph has only even vertices, then we can find an Euler circuit for it, right? Obviously. But the way that we do that is by beginning at any vertex and traveling over consecutive edges according to these rules. So these are the rules. So rule 1, after you have traveled over an edge, erase it. If all the edges for a particular vertex have been erased, then erase that vertex also. And then number 2, travel over an edge that is a bridge only if there is no alternative. Okay, so really step 2 is kind of the key, because when we were doing this one and we got to this point where we were at F, I decided not to go down here. Why? Because this edge is a bridge, isn't it? If we take this edge away, then we end up with a disconnected graph. And the reason you don't want to travel over a bridge unless there's no other choice is because once you've crossed that bridge, there's no way to get back, right? So number 2 is really the key there. Let's practice. I should have given myself more space, I guess, because I kind of want to, well, I kind of want to redraw this. Anyway, but assume that you're doing maintenance work along pathways joining locations A through K in a theme park. So these are a whole bunch of different locations in the theme park, and they're connected, in this, using this kind of relationship. We're asked to find an Euler circuit. Excuse me. We're asked to find an Euler circuit in this graph to make our job efficient by not retracing pathways. Assume that you leave from and return to building C. So this is going to be our starting and ending point right here is point C. Okay, so once I use an edge, I'm going to delete it. So rather than rewriting the whole thing, I might just like scratch it out once I've used it so that I know that I can't use it again. Or I'll just trace it, I guess. But anyway, so from C, I keep going this way because I'm kind of inclined to want to go towards A. Can I do that? Yeah, it's not a bridge, right? This is not a bridge. If I remove it, I still have a connected graph. So I can go here, right? That's not the only option, right? But that's just what I chose to do. Okay, so I can go there. And once I'm there, I have no choice. I have to go down here. Okay, and I'm going to pretend that those things don't exist anymore, right? So vertex A doesn't exist, and neither do these two edges that I've shaded in. So now I get to B, and I can take any course that I want as long as I don't cross a bridge. And by the way, I might want to write down my Euler circuit. So I started at C, and then I went to A, and then I went to B. So now at B, I could go this way, right? If I remove that, I don't have a disconnected graph. If I remove this, I don't have a disconnected graph. If I remove this, I don't have a disconnected graph. So I could go any way, really. Maybe let's go down to E. Once I'm there, I have no choice. I've got to get back up here. So I'm back to C now. But now I have some choices. I should only cross a bridge if I have no other choice. Well, if I take away this segment, I don't have a disconnected graph, right? I would have this graph right here that's kind of like a W, so it's not disconnected. If I take away this segment, still not disconnected, right? If I take away this one, not disconnected. Take away this one, not so I can go any way I want. Let me fill in this stuff. So I'm going to come back over, and then down, and then back up. Okay, now I pretend that all that stuff doesn't exist anymore. And what do I do from here? Again, I could go either way. If I remove this, this is not a bridge, this is not a bridge. So I can go down this way to J, this way to K, this way to I. Okay, and now I'm pretending that these edges don't exist and that K and I don't exist anymore. So really all I have left is what is not shaded in. So do I get any bridges? I don't think so. If I remove this, still connected. If I remove this, still connected. If I remove this edge, it's still connected. So I think I can go any way I want. I'm going to go up to H. And then I have no choice. So I have to go down to F. Okay, now at this point, I do have a bridge, right? This segment is a bridge. If I remove it, then C, then I have no way to get to C. So I'm not going to cross that bridge. I have to make a different choice. I could go up this way or over this way, right? Neither one of these are bridges. So I don't know. Let's say that I choose to go this way. Then I have to go back up, and then back down, and finally I can end back where I started, at C. Okay? So that's how Flurries algorithm works. When you get to once you've crossed an edge, you pretend that it doesn't exist anymore, right? And then you ask yourself, am I crossing a bridge? And if you are, don't do it, right? Unless there's no other choice, right? You only cross a bridge if there's no other choice available to you. Okay, so I've got 3 more examples to show you of maybe some ways that this stuff could be useful in the real world. So number 5 says a tour company wants to design a tour that travels every street in the map below. So maybe this is some downtown area of some kind of famous city, and the tour wants to go down every possible street. Okay. They want to begin and end the tour at the same location and minimize traveling over any street more than once. So they're not saying that they won't travel over a street more than once. They just want to keep that to a minimum. So we want to find a route for them by Eulerizing the graph. So you can kind of think of this like a graph, right? Where each of the corners or intersections is a vertex, we'll say. Right, so that I don't have to redraw the whole thing, I'm just going to draw the vertex or the vertices there. Okay, and we can label these A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. This is not Eulerian. Notice that you've got degree 3 here, degree 3 there, degree 3 there. Right? So you've got at least 3 vertices with, you've got at least 3 odd vertices. So there's not an Euler path. There's definitely not an Euler circuit. But what we can do is we can Eulerize the graph. We're going to Eulerize the graph. And what we mean by that is we're going to add the fewest number of edges possible to the graph in order for the graph to have an Euler circuit. How do we do that? Well, every odd vertex, we're going to add an edge to it so that it becomes an even vertex. So maybe I do need to redraw this so that you can see what I'm talking about. C, D, E, F, G, H, I, J, K, L, M, N, O. So A, E, F, G, H, I, J, K, L, M, N, O. Okay. Okay, so this is the situation, and we're going to have to add a couple of edges. Right? So for example, right here we have 3 edges, and right here we have 3 edges. So what I'm going to do is add another edge. Now I have 1, 2, 3, 4, 1, 2, 3, 4. So that fixes up quite a bit there. Where else do I have issues? So 2, 2, 1, 2, 3. So that's an issue. Here I have 1, 2, 3. So that's also an issue. 1, 2, 3. So that's an issue. So I think I'll do another bridge or another edge here. So now I've got 1, 2, 3, 4, and 1, 2, 3, 4. 2, 4, 3, 3. So I'll have to add another edge here. So now I've got 1, 2, 3, 4, 1, 2, 3, 4. 2. Here I've got 3, 1, 2, 3, 4, 4, and 3, 1, 2, 3. So these are my last 2 issues. I think if I connect them, I mean ultimately they have to travel along the street, so we can't just pretend that there's a street connecting G and K. So really they'd have to go from here to here, which makes this 4, but it makes this 5 now. 1, 2, 3, 4, 5. But then I can add another bridge from here. Not a bridge, I keep calling them bridges, but another edge. And now I've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So everything should have an even number. All of the vertices should be even now. And once you get that, then you know for a fact that you can draw an Euler circuit. And it doesn't really matter where you start. Okay? So if I decide to start at A, I can go from A to B. And then I can go from B to C. Maybe along that. I mean, really, I'm just going to go along the street. Then I can go from C to D. From D to K. From K, I have some options. Doesn't really matter which way I go. I'm going to head back up. So I'm going to go from K to J, from J to G, from G to C, from C to B. So I'm going to travel along the same street again, okay, but backwards. That's all right. Now what? Now maybe I'll go from B to F, from F to G. Why not? From G, I'm going to travel down along the same street, okay, from G to J, from J back to K, so traveling along the same street again, from K to O, from O to N, from N back up to J. Okay, I'm feeling pretty good about this so far. Okay, where should I go from there? Well, I've only got one option, from J to I. From I, I'm not going to get any bridges. I don't have any bridges, so it doesn't matter which way. Maybe I'll go from I to F. From F, I've got to go over to E. I've got no other choice. Okay, and now notice I can't go up to A. That's a bridge now. So I can't go that way. So I've got to go down to H. This is a bridge, isn't it? If I take it out, no, it's not a bridge. I could still get to I. That's not a bridge. Okay, so I'll go over there then. I to M, M to N, N back to M. That's not a very interesting tour, I guess. M to L, L to H, H to E, and then E to A. Goodness gracious. But there you go. There's your Euler circuit, right? And you only had to cross the same street 1, 2, 3, 4, 5 times. Right? So there were 5 repeated streets in the tour, but I mean, given the number of streets you're going down, that's not too bad. How many did we go down? 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, so almost 30. So to only have to backtrack 5 times, not bad. It's not bad. Okay. Here's another example. This one says, model the map of South America by a graph and use this graph to color the map using at most 4 colors. Okay. So the idea is that when we color in this map, we only want to be able to use we only want to use 4 colors such that no country is bordered with another country that has the same color. So I think what we should do is draw a graph that shows the relationship between countries that have borders. Brazil, you'll notice, has a border with like every other country except Ecuador. So Brazil is kind of a key here. But let's see if we can make a graph out of this. So I'm going to put Brazil kind of over out here by itself because I think I'm going to have a bunch of edges coming out of Brazil. I'm going to have French Guiana, Suriname. So French Guiana, Suriname, British Guiana. I've already used B for Brazil, so maybe I'll call this G for British Guiana. Or Guyana, however you say that. Venezuela. Colombia. Ecuador. Peru. Oh, and I guess Chile, right? So Brazil also doesn't border Chile, right? Peru, Bolivia. Oh, I've already used B for Brazil. So Bolivia. O for Bolivia. Peru, Bolivia, Chile. Then I've got Argentina, Paraguay, and Uruguay. And I think that's all of them. Okay, so I'm going to draw a connection between all of the countries that border each other. So for example, Brazil has a border with French Guiana, and with Suriname, and with British Guiana, and with Venezuela, and with Colombia. Oh, I used C twice. Maybe I'll call this CO for Colombia and CH for Chile. But it has a border with Colombia. It has a border with... It does not have a border with Ecuador. It has a border with Peru. It has a border with Bolivia. It does not have a border with Chile. It does have a border with Argentina. See this little piece right here? It's got a border with Paraguay. It's got a border with Uruguay. Okay, what else? Well, French Guiana has a border with Brazil, which we've already got represented. It also has a border with Suriname. British Guiana has a border with Brazil, with Suriname, and with Venezuela. Oh, and I guess I skipped over Suriname, which has a border with British Guiana and French Guiana and Brazil. So that one's good. Venezuela has a border with Colombia, British Guiana, and Brazil. Ecuador has a border with Colombia and Peru, but not with Brazil. Peru has a border with Ecuador, Brazil, Bolivia, and Chile. Okay. Bolivia has borders with Peru, Chile, Argentina, Paraguay, and Brazil. Okay. Chile has borders with Peru. Bolivia and Argentina. Argentina has borders with Chile, Bolivia, Paraguay, Brazil, and Uruguay. Oh, and I used Paraguay. I used P twice. So Peru. Okay. Paraguay has borders with Argentina, Bolivia, which I've already got on there, Brazil, which I've already got on there, Bolivia, Argentina, and Brazil. I think that's it. Uruguay has borders with Argentina and Brazil, and I think that's it for that one. Okay, so I think that's our graph. I could have definitely drawn this a little bit better, right? But anyway, so is it possible to color in this map with only 4 colors? So now we have to answer the next part of the question. So what I'll do is I'll just start. So I'm just going to start by putting a color. Like I'll circle each of these with a color. And I'm not allowed to circle any two letters that use or that are connected. Any two vertices that have an edge connecting them can't use the same color. So I'm going to use red here, which means I can't use red really anywhere else, right? Or rather, I can't use red with S, and I can't use red with B. But I could use red with G. That would be fine. So now with G, I can't use red with V or S or B, but I could use red with Columbia. With Columbia, I can't use red now with V or with B or with E, but I could use it with PE. Now this one I can't use red with E or B or Chile or Bolivia. So I can't use that one or that one or that one or that one, but I could do it here. This one I can't use there, I can't use it there, I can't use it there, I can't use it there, and I can't use it there. So that's all that I can do with red. Let's move on to blue. So I'm going to go ahead and say blue for Brazil. That's going to knock out a whole bunch of possibilities because I can't use blue here or here. I could use blue here. Okay, not a problem with that. I can't use it here or here. Chile is the only other one not connected to Brazil, so I'm going to go ahead and color Chile in blue as well. And that exhausts all that I can do with blue. Let's move on to green. So green, I can use green here, but then I can't use it here, here, or here, but I've already colored those in. I could use it here. Can I use it here? Yeah, blue there, red there. I don't have a color assigned here yet. Red there, so yeah, I can use green there. Here I can't use green, but here I can. This is connected to blue, it's connected to a red, and that's it. So green. So then finally this last one I can color in with like a light blue type of color. Okay, and there you go. So I could go back to the map now and color them in with their corresponding colors. So I know that Paraguay has to be in this like light blue color. By the way, this isn't the only. Oh, this isn't going to turn out very well. They're all going to look funky, but this isn't the only way that you could have come up with mapping, right? But Suriname. See, those colors look the same, but they weren't. Venezuela. Anyway, you get the idea. Venezuela, Bolivia. See, they look the same, but they're they're not. This one was this color, and the ones I'm drawing right now are this other color. But anyway, Uruguay, we could do with green. Red was this. Colombia, Peru, Argentina. And then the last color was the dark blue, which I did Brazil, Ecuador, and Chile in blue. Okay, well, so that's the idea there. But you'll notice that you don't ever get like colors touching. Again, this was green, and this one was like a light blue color. You just can't tell the difference on the page. But anyway, so that's that. So another use of graph theory, right? In fact, this is a generalizable thing. It turns out that any map is colorizable with just 4 colors. You can draw the craziest map you can think of, and 4 colors is enough to color it in. So here's an interesting video. I'll put a link to it where I post the rest of this stuff so you can see what I'm saying. But it's an interesting thing. Definitely take a look at that. Okay? All right, last example. It says, each member of a city council usually serves on several committees to oversee the operation of various aspects of city government. Assume that council members serve on the following committees: police, parks, sanitation, finance, development, streets, fire department, and public relations. Determine a conflict-free schedule for the meetings. So the way this chart works, it says committee, and then it has members in common with. So the police committee has members in common with the public relations and fire department committees. The parks committee has members in common with the streets and development committees, and so forth. So I'm going to model this again with a graph. Maybe I'll just label it like this: A, B, C, D, E, F, and G. So A, B, C, D, E, F, and G. Something like that. And then I'm going to draw an edge connecting any committees that have members in common. So like the police committee, for example, that was A. That's bad labeling system. It's going to get confusing. But police has public relations. Shoot, this doesn't even list all of them. So I need to have one for public relations too. So maybe public relations will be H. So public relations is H. Public relations, fire department, streets, development, fire department, parks, police, public relations, streets, fire department, public relations, and finance. Okay, the rest of them are all on there. Okay, anyway, so police have members in common with public relations and with the fire department, which is G. Okay, parks, which is B, has streets, which is F, and development, which is E. Sanitation, which is C, has fire department, which is G, fire department, and parks, which is B. Finance, which is D, has police, which is A. Police and public relations, which is H. Development, which is E, has streets in common, which is F. Streets, which is F, has fire department, which is G. And public relations, which is H. And then finally, the fire department, G, has finance, which is D, in common. Okay, so there's our graph. Okay, so we're supposed to use this graph to determine a conflict-free schedule for the meetings. Goodness gracious. A conflict-free schedule. So you can also do this with a coloring system. Like whatever time B meets at, like let's say that red represents like an 8 a.m. meeting, right? And let's say that B meets at 8 a.m. Then that means that C, E, and F cannot also meet at 8 a.m. So I can't color C, E, and F in red, okay? Because they have members in common. So I can't do I can't do C, E, and F. I could do D though. If I do D, I can't have A, H, or G. And from this one, I couldn't do C, E, or F, A, H, or G. So that takes care of all of them. So I can't do any more at 8 a.m. I can only do B and D. If blue represents a 9 a.m. meeting, I could do C in blue. Then I just can't do B or G, but I could do E. If I do E, I can't do B or F, and I already couldn't do G because of this one, but I could do H at that time. And then if I do H, I can't do A, so that takes care of all of the 9 a.m. meetings. I can do C, E, and H at 9 a.m. And then if green represents 10 a.m., I can do F, but then I can't do G. But I could do A. So I could do F and A at 10 a.m. And finally, G can take place at 11 a.m. Whoops, 11 a.m. could be G. And by the way, these all correspond to these letters. So the parks and finance departments can meet at the same time. They can meet at 8 a.m. The sanitation, development, and public relations departments can meet at the same time. They can meet at 9. The streets and police can both meet at the same time. They can meet at 10. And the fire department can meet at 11. Right? That would be a schedule-free conflict, or a conflict-free schedule for the meetings. Anyway, so that's the idea. Kind of a long section, long lecture. I apologize, but that's that.